All right. So last time we were looking at, we found this nice formula for the directional derivative, right? And we started looking at the directional derivative and the gradient, and I have some sort of images and problems to show you today. I just want to talk more about the gradient a little more carefully and do some example problems and stuff. So let's do that. Okay. Yeah, so there's this special vector called the gradient, but it's a vector. You pick a function and a point and a direction. So you have to pick like three things, and then you can define the gradient of that function at that point. Sorry, no, the direction is for the directional derivative. Function at a point, you get the gradient. And then you pick a direction, you can use the gradient to compute the directional derivative. So let's just remind ourselves. So today's the 2D gradient. We'll do the 3D gradient on Wednesday. Let's talk about these for a little bit. Just kind of recap what we discovered on Friday over Zoom. So given z equals f of x comma y, the gradient of f is the vector sort of partial x times I plus partial y times j, which, makes some sense to make a vector like that because we've got two partials, and when we have two numbers, we can package them together into a vector. And we write, like I've said, we either write grad f or this upside down triangle f for the gradient. And so just as an example, I mean, this is no harder than computing partials, but f of xy is like x cubed y plus x squared y squared, right? Then the partial x is 3x squared y plus 2xy squared. I think you just differentiate the x and the two x's, right? You guys agree with that? The partial y is just x cubed plus 2x squared y. And so the gradient is just this vector where we put these together. So it's a general vector. Actually, I really should call it, it's really called a vector field, which I'll show you pictures of at some point. So there's this word field. But at a specific point, it's going to be a specific vector. So let me just say, sort of the generic gradient then is just, I'm just going to write these down. Just looks kind of complicated, but at any point, if we wanted at the point, say, I don't know, like 1, 2, right? If we wanted to pick a specific point, because now the thing you think about is like, this is a vector at every point x comma y, you're supposed to think of this vector sticking out of that point. And it's going to tell us something about the graph at that point, the graph of f at that point, or the nature, the way that f is changing at that point. So this is a vector sticking out of xy of x comma y at every x comma y in the plane. And that's why I said that's called a vector field. You can imagine like plotting these for a bunch of different points, you're going to get some sort of, arrows all over the place, right? So for example, if we just do the point 1, 2, so that's how you write this. We actually want to plug in a specific point. It's kind of like a function, right? It's like a function, but it's a function where the output is a vector instead of a number. So we just get, 3 times 1 squared times 2 plus 2 times 1 times 2 squared I plus 1 cubed plus 2 times 1 squared times 2 j. I'm plugging those in correctly. Let me know if I'm not. So what does that work out to be? I don't know, check my math, but I'm thinking 11i and 5j. Really, all I did was compute the two partials at that point and put them into a vector, right? Did I mess up somewhere? Okay. Is that people checking my math? Is it 14i? Did I mess up? Oh, that's a 2, isn't it, right there? Thank you. That's a 6 plus 8. It's 14. Thank you. Yeah, I knew I must have messed up. I did that too fast. I hope I did these derivatives right. You guys aren't just trusting. I'm just trying to show you an example. And the thing is, the gradient is important, right? Everything else looks okay? Okay, thank you. Gradient's important, right? Because it's, well, first off, it lets us compute directional derivatives. Gradient is important for a number of reasons. One is lets us compute directional derivatives easily. Directional derivatives easily. So I gave you this. So right, so the directional derivative of f at p in the direction u. So now I'm at a specific point and I want to go a specific direction away from that point. And I want to ask what's the slope? Basically, what's the rate of change, instantaneous rate of change in that direction? And remember, this is a unit vector. Is so it's this, remember I said it was fu p, and it's given by the gradient of f at p. That vector dotted with u. That's sort of what we discovered. We sort of factored that formula. We came up with that slope formula as just delta z over delta horizontal, change in z over the change in x and y. And we actually factored that formula and realized it looked like it was actually factors the dot product. And we got this, right? So this is the directional derivative formula. And as an example, if we look at this same function at this point, but let's pick a direction. So example, so f of x comma y is x cubed y plus x squared y squared. P is the point 1, 2. And let's just say the direction is something like, I don't know, let's go in the point 1, 2. Let's go in the 2, -3 direction. 2i minus 3j. Right, so you can imagine being at that point and leaving in that direction and asking yourself, like, what's the slope in that direction? So like, because we're on a graph, we can think about leaning on the tangent plane. And you zoom in, it basically becomes the tangent plane, and you sort of say, well, okay, if I'm on this ramp and I go off in some direction, what's my slope in that direction? Right? Now, what do I need to do here before I compute this? we already know this piece, right? But can I just plug in this vector right here? What do I have to do to it? Scale it down to length 1, right? So you can pick a direction just to it's sort of easy to say, just go in that direction, but you'd have to scale it to be length 1. So we already found the gradient of f at p at p is 14i plus 5j. And so then, but then we have to scale the direction vector to be a unit vector. And then we can compute directional derivative. I mean, you're gonna often end up with these square roots in the bottom because you're dividing by the magnitude of the vector, right? So your numbers may not be that nice, but it's still, you know, a good. It's a number. It's a slope. It's the right slope. You're computing the correct slope. So, okay, so then scale 2i minus 3j to a unit vector. So we get u is 2i minus 3j divided by the square root of 2 squared plus negative 3 quantity squared, right? What did I do? Oh, I didn't write 2 squared, thank you. Yeah. So what is that, root 13? So this is basically, you could just write it as 1 over root 13 times 2i minus 3j. I mean, you could write it as, you can write 2 over root 13i minus 3 over root 13j if you want, but sometimes it's nicer just to leave the factor outside because then the directional derivative is just the dot product And the nice thing is the 1 over root 13 can just come out in front. And then you get 14 times 2 plus 5 times negative 3, right? Dotting them together. 28 minus 15 is, oh my God, I did not do that on purpose. 28 minus 15 is 13, right? Again, I might have messed up. Did I do that right? That's totally unintentional, but it works out to be 1 over root 13 times 13, which is root 13, which is, 3 point something. Yeah, that was completely coincidence. Good. Make sense of what we're doing when we compute directional derivatives? Fairly straightforward. Okay, so that's the first big usefulness of the gradient. The second is that it has this geometric interpretation, right? So let me know if you have any questions about anything I did up to that point. Two is geometric, I'll say interpretations. There's actually a number of there's a lot of information we get out of the gradient. So, and the thing is we can use the formula. This is sort of what I was saying last time, where it's once we have this formula, we can actually use the geometric definition of the dot product to put a cosine in there. And then that tells us something qualitative. So fu at p is the gradient of f at p dotted with u, but with the geometric interpretation of the derivative, right, of the dot product, sorry. That's the same thing as the gradient, as the magnitude of this gradient vector times the magnitude of u times cos theta, right? We've seen that over and over again. And a lot of times now we've seen a couple different cases. We saw some projections where like this is length 1, and that actually is helpful because it makes it something you can interpret nicely, right? This is just a 1. And so we get this so another way to think about the directional derivative is it's just the magnitude of the gradient times the cosine of the angle, where theta is the angle between the gradient and u. So I should draw a schematic of that. So, you know, the gradient could point in whatever direction you want, depending on the point you're at. And then u could point in some direction. And then we're looking at the angle, this is the angle between them, right? And this sort of tells you something about how the directional derivative changes as you sort of move away. I mean, honestly, it's this ramp thing that I was trying to show you over Zoom before, right? So it's like you really want to think that you're on some ramp. You zoomed in on the graph. You're on it. It's basically it becomes a ramp, like a tangent plane. And now the gradient, you can, well, I'll write this down, but the most cosine could be is 1. And that's when these two are pointing in the same direction, right? So that means if I go in this, if I want, this direction right here is the direction where I would go straight up the ramp, yeah? If I'm just like pointing directly into the ramp. That's direction straight up the ramp. So that actually is the gradient direction. And then as you turn away from the gradient direction, it basically goes, the slope goes down like cosine. So when you get to 90 degrees, it's 0. But also when you get to 60 degrees, it's a half, like cosine of 60 is a half. So it's half the slope at a 60-degree angle with this direction. So like there's just interesting things to think about, like as you sort of spin around the direction that you could go in. It's like this direction straight up the ramp, this direction straight down the ramp, these two directions 0. And then it changes like cosine in between, right? That's that data we plotted. That's what I was having you guys do with that data, is plot all that. So in particular, this is what I was saying last time. This feels like it's important, so I wanted to recap it all. In particular, the directional derivative at a point, it's between, like the most this could be is this. It's you know, it could be the magnitude of the gradient, and it could be, but the least it could be is if this is -1. So it could be negative the magnitude of the gradient. Right, so that's basically the directional derivative is between those two values. So you see what I'm saying? Just because cosine is between -1 and 1, that means this number is between minus the magnitude of the gradient and plus the magnitude of the gradient, because you're just multiplying by the cosine. So in our example, like that says that like if we actually take this example of like what we found the gradient was 14i plus 5j at this point, that the max slope is that magnitude of that. So just leave this on the board. This last line here. So yeah, so for example, we had the gradient being 14i minus 5 plus 5j. The magnitude of that is the square root of 14 squared plus 5 squared. What is that? 196 plus 25 is 221. 21? Yeah, 221. It's just under 15. 225 is 15 squared. So it's like, you know, it's about 14.9 something. And so that's what I'm saying is like, basically, again, these slopes are pretty steep, but at this point on this graph, it's pretty steep, right? Like I was sort of saying how like the gradient tells you the tilt of the tangent plane and its orientation. So this is saying the maximum directional derivative is like 14.5. So there's direction where if you go straight up the ramp, that's your rate of change. It's like 14.5. So you're going up pretty steeply, right? Okay, or 14.9, sorry. Whatever that is. I just made this number up. I know it's close to 15, so. Yeah, so like, and that's saying is that this is the maximum directional derivative. And it's achieved when theta is 0, right? When theta up there is 0, because that's when cosine of theta equals 1. In other words, when u points in the direction of when u points in the same direction as the gradient, i.e., when u points in the same direction as the gradient, so what that tells us is it's kind of this picture I had mentioned, or I had shown you at the end of class on Friday, right? That basically the maximal FU is when theta is 0, is when the u points in the same direction as the gradient. And otherwise, it's just governed by cosine. So that's when it's going at 90-degree angle, it's cosine of pi over 2, which is 0. When it's going opposite of the gradient, it's cosine of pi, which is -1. And again, that does it make sense with the ramp? That like, if I'm going this direction, that's the maximal ascent. So if I turn 90 degrees, I'm just kind of following the same height on the ramp. And then if I turn the whole 180 degrees, I'm basically going down the ramp. Okay, so yeah, and so that's kind of what this means is that like, let me just write this on the board that, so what we found basically is that, it's a vector, it's sort of what I was saying last time, it's a vector, gradient's a vector. It has a magnitude and a direction. Vectors always have magnitudes and directions. And those both have interpretations. So to sum up, I think I wrote something very similar in class last time, but I'm just trying to, it's just really important. So I'm going to go over it. I'm just going through it a couple of times. So the gradient is a vector. So it has magnitude and direction. And both of these have interpretations and direction, both of which have qualitative meaning. Qualitative meaning. So like I said, here the direction, well, the magnitude is the maximal directional derivative. We said this is the, like in this example, right? So the magnitude is the maximal directional derivative at that point. And the direction is the direction of the maximal, increase. So actually, this is super important because it's almost like a little recipe that tells you at every point, like it tells you at every point, go this direction to go up the fastest. And then this is how fast you'd be going up at that point. In fact, in like optimization techniques, a lot of times if you're trying to find a maximum value of a function in some complicated situation where you can't just look at a graph and point at it, there's all these techniques using the gradient where you basically follow the gradient. You're trying to find your way around. You're trying to find a maximum value of this function. And so you start at a point, you compute the gradient, you say, okay, I'm gonna go that way a little while. Go that way a little while, you compute the gradient again, you follow that a little while. And then eventually, the hope is that eventually you'll sort of like find the max. So if you take like Professor Levy, who teaches this optimization class, this 2000 level class, he does all these gradient techniques where he does this. Okay. Okay, last geometric interpretation, this is sort of new, is that if you think about like, again, this is like, we're thinking about this picture and the ramp, right? That this is like a top view of a ramp. This is like looking down from above on this ramp right here. And what it's saying is that the ramp is tilted that way, right? It's tilted sort of like, if you're looking at the top view down from above, right? If I orient it some way, it's gonna be like that, because that's the direction to go up the fastest. Does that make sense? It also means that you could imagine this living in the contour map, and that the contour, if you're following a contour, you're neither going up nor down, right? If you follow a contour, you're staying at the same height. So you can actually think about the contour here is actually just like a line. Again, we're zoomed way in, so contours are all straight lines now. And I claim that the contour would basically be this line right here connecting these 2 points going through the center here. Right, because that would be the directions to go, those are the directions you go where you don't go up or down. So the contour would pass, the level curve would pass through this point like this. In particular, that's perpendicular to the gradient. So the gradient is actually perpendicular to level curves. That's the last sort of geometric interpretation. So I've got these two interpretations there, and then notice also, and I'll give another argument later once we've done the multivariable chain rule. There's sort of a mathematical argument, but just from pictures, you can sort of tell that we've got those two. Maybe I should say, let's put bullet points here. This is like bullet point 1, bullet point 2, and then bullet point 3 is that the gradient is perpendicular. Grad f at P is perpendicular to the level curve through P. Okay. The level curve of F through P. And so you could look at a contour map and just basically draw the gradient vectors. Right, so just as an, like I could actually do this, like say, just draw kind of a picture like I've done before. If I just draw some sort of like, I don't know, some sort of imagine this is some contour map. So this is a contour map of some function. Let me label these contours. Let's just say this is height 5, 6. What am I doing? 7. I guess this is a hill, so it's like that, right? Sort of saying this is some peak and then it's going down on either side, something like that. Then I can just start drawing gradient vectors all over the place. Like the gradient vector is always perpendicular to the level curves. Now I'm not getting the length right because I'm just trying to draw them in the picture, but I'm just drawing the direction, right? So maybe there's some little peak right here. You know, maybe there's another little height 8 peak there. And so they're all sort of pointing. Does this make sense? Please just start talking if you have a question, since I'm not pointing, so I'm not looking at you guys right now. Right, these are all the direction maximal, yeah. Well, this would be like the top, if this is like a topographical map, there would be like a little mountain peak in the middle here. And so they're all kind of pointing towards that peak, and not exactly pointing towards, sometimes like this isn't pointing exactly towards, but because it's always perpendicular to level curves. But it is that thing, if you follow gradients, you're basically going up towards like mountain peaks, right? So the gradient, so the red arrows are gradient arrows at every point, perpendicular to the contours. Right. I mean, it gets a little wonky in here. You know, I guess somehow, like if you're in here, there's probably more, you know, like 6.5 might be something like that more, and then there's some weirdness going on, like, but does that make some sense what I'm talking about? That's good. So like it could, right. So it's because the gradient direction is the direction of maximal increase. So they're actually always pointing in the positive direction. A lot of times in physics, you actually see the negative gradient because you want to think about like, if I dropped a bunch of marbles on here, they would like flow downhill. And so you want to look at their flow downhill. And so if I drop a marble on this ramp, it's going to go in the direction of maximal negative. It's going to go down the ramp. If I put a marble here and let it go, it's not going to take off in that direction, right? It's going to go straight down the ramp. And so a lot of times the negative gradient is sort of like how particles would flow in this situation. Like if you drop them on this sort of like landscape, and they would flow downhill. Does that make sense? So yeah, they're perpendicular. So that's a good point, and they're pointing in the increasing direction. In the increasing z direction. Okay, good. Other questions? Oh, I didn't stop the share. That was dumb. Sorry. Sorry, anybody watching this video later. This is what I was talking about, that the arrows point perpendicular to level curves in the direction of increasing z. Like that, okay. Sorry. Okay. Now, there's some also directional derivative stuff. This is a gradient, but I wanted to go back to a little bit of directional derivative. There's two different points I want to make, I guess, for the rest of class. So one is this. This is an example from the book, and it's a qualitative example, and it says, you know, just say whether the directional derivative in the indicated direction is positive, negative, or 0, right? So I guess from each point, there's two different directions. There's this W direction, the V direction, which they give as I plus 2j and 2i plus j, although if you're going to compute directional derivatives, you'd want to scale those to be length 1. Now, the book's answers are a little wonky. In fact, I disagree with their answers to this one. And I keep hoping they're going to change it in the new edition. I really should email the authors and tell them I disagree with their answer to this. But let's go through it. So The easier one here is W. Like if you leave this point, it's kind of like the stuff we were doing with partials, where you're asking for the sign of the partial derivative, right? Except instead of just going pure east or pure north, do east or do north, you're just going on whatever direction they're telling you to go. So like if I leave this point and go in the direction W, is that increasing or decreasing? It's increasing, right? You left the 4 contour, you're now between the 4 and 5 contour. So you're at like 4, if you move over a tiny bit, you're at like something a little more than 4, so you've increased. The V is questionable. You could argue it's not quite tangent. If it was tangent to the contour, the directional derivative would be 0, because you'd be basically following the contour. I think the book says they're both positive. So I think V is meant to be a little bit, not quite tangent, it's a little bit tilted, you know. This one, similar arguments, right? W is positive, V is negative, yeah. Again, you have to be careful not to think of it as like leaving the 6 contour, because that's pointing towards another 6 contour, but it's just the fact that it's between 5 and 6, right? Is what's important. You're in the area between 5 and 6. Now this one's interesting. The book says both of these are negative, which makes a lot of sense because you're leaving the 10 contour and going towards the 9 contour, right? But it's also a 9 contour over here. And so the one thing we have to be a little bit careful about is something like the following. Like imagine you're on a y equals f of x graph, and I'm at this point, right? If I move over a little bit, certainly it's decreasing, right? If I move over that way a little bit, if I move over this way a little bit, it's decreasing. But what's the derivative at this point? It's 0, right? The derivative is 0. Because it's decreasing on both sides. So you're actually at a max, and so the tangent line is horizontal. So the fact that this is a maximum, like if these were 11, 12, 13, 14, I would agree. These are both negative directional derivatives. But I actually think that at this point, it's like the top of a ridge line. Does that make sense? Like you're going up from here, you get to this top of this ridge, and then you go down. So to me there, the directional derivatives are actually 0 in every direction. If you have a horizontal tangent plane, then the directional derivative is 0 in every direction. And here I think the tangent plane would be horizontal because I think 10 would be a peak, would be a local maximum. Yeah. I don't think so, because if you zoom in enough, it becomes kind of a straight line, you know? I mean, it's an interesting point. It is weird. It's definitely different from this in that we're not used to having a whole, like, it's like everything on the 10 contour would be a maximum. You know, it's not just like a one mountain peak. But you could argue the same thing here, like at this point right in the center, sorry, let me stop this share. At this point right in the center of this, where this peak would be, it's like, well, what's the gradient at that point? Well, I claim it's 0 because the partials, you know, there's nowhere to go up anymore if you're at that point right in the middle there. And so you're already at the top. Every way you go, you'd go down. The tangent plane would actually be horizontal right there, just like the tangent line would be horizontal here. And so the gradient is actually 0 at a point like that, like at a maximum point. In fact, one of the things we're going to do shortly is optimization, finding maxes and mins. And usually when you do that, you set the derivative equal to 0. Here we're going to set the gradient equal to 0. So we're going to set both partials equal to 0. And then find the points where like the peaks and valleys are achieved. But anyways, this example on the screen is a little bit of a weird one. Like, I really think I did check this most recent edition, and they still say these are both negative. And I just feel like that can't be right. They have to be 0, but I don't know. Makes some sense. Okay, and then another thing, I often give this as a homework problem, but it confuses the hell out of students, and so now I've just decided to do it in class. because it's a nice one. I like this problem a lot. There's a lot going on here. So you are climbing a mountain. Did I share screen or not? No, I didn't share screen. Sorry. You are climbing a mountain by the steepest route at a slope of 20 degrees. When you come upon a trail branching off at a 30-degree angle from yours, what is the angle of ascent of the branch trail? There's like multiple angles here. Like, what on earth is going on? I mean, you can sort of imagine this, right? You're like, again, you're on a, just think about yourself. I mean, you're supposed to idealize this and say you're on a ramp. You know, when you zoom in, it's basically a flat ramp. And then the slope is 20 degrees. So that's like the tilt of this is 20 degrees, right, above. But then it says you have a trail branching off at an angle of 30 degrees. So now, like, if you look at the top view of this, there's a 30-degree angle here. You're branching off in that direction. And you want to know the angle of ascent in that direction, right? If the branch had been 90 degrees, what would be your angle of ascent? If I go 90 degrees off from the steepest ascent, what's my angle of ascent? Say it. 0, right? You're not going up or down. If it's 90 degrees, you wouldn't be going up or down. And if you go 180 degrees, you'd be going down 20 degrees, right? So the question is, yeah, it's a weird problem. It's like, there's two angles here. What I think there is, so mountain problem. Stop the share again. Just only have about 10 minutes left, so I might do this a little bit quickly. So the steepest route is 20-degree slope, like a grade, right? That's kind of what the 20-degree slope. So what that means is that we can draw kind of like a side view, right? This is like a side view of the mountain. Maybe I don't want this. It's just like we're on the side of the mountain. And that says that this angle is 20 degrees, right? Then we have a top view where you are standing here and you're going, say, that way. And it says there's a trail branching off at 30 degrees from that. So it's like looking down on you from above. So you're just walking up this mountain, but then there's a trail that branches off that way, right? Didn't have to be straight up, I don't know. So maximal direction of ascent, bless you. I guess this is like the main trail. And this is the branch trail. Okay, so there's a couple of things going on here. One is how to go from the angle of ascent to the actual slope. How would I get the actual slope of this if I know the angle here is 20 degrees? How do I get rise over run? Yeah. Yeah, well, I think it's actually tangent in this case. You're right, but it's like, if I knew the rise over run and I didn't understand, I get the angle. So if I do tangent of 20 degrees, I actually get the opposite over adjacent, the rise over run. Good, so tangent of 20 is actually the rate of ascent, not the slope of ascent, right? So yeah, so rise over, okay, so rise over run. Rate of ascent equals rise over run equals the tangent of 20 degrees, which is, let's just ask, 10 This gives 0.364. It's about 0.364. So that's the maximal rate of ascent, right? So that's saying what this is sloped, whatever this slope, this is the tilt of this is like 0.3, whatever that is, right? 0.364. So now what if I go off on the 30-degree branch path? How am I gonna compute that rate of ascent? This is my maximum rate of ascent, and I want to go 30 degrees off from it. What am I gonna do? I'm giving you guys maximal FU. Okay, right? That's the maximal directional derivative. It's basically straight up the mountain. And so what did we say? How do we really want the directional derivative in the direction that's 30 degrees off. So how do we do that? Multiply by cosine of 30, right? This is basically like, yeah, we want the directional derivative at an angle of 30 degrees from the max FU. So yeah, that's really the thing. Like this, you could think of this as the magnitude of the gradient at this point. This really is the magnitude of the gradient at this point, right? Because that's the maximal directional derivative equals magnitude of the gradient at this point. And then we know that the general FU is the magnitude of the gradient, I guess at P, is the magnitude of the gradient times the cosine of the angle. So in this case, it's 30 degrees. And so we take this number and multiply it by cosine of 30. So times cosine, 30. Oh, geez Louise. No, I don't know if this is going to work. 30 degrees. Am I in degrees? I can't tell. I must be in degree mode. You know, it's root 3 over 2. That's 0.7. All right. No, root 3 over 2 is about 0.85. It's about 85% of 36. That's plausible. Okay, so that's I think I'm in degree, but so that's about 0.315. That is now the rate of the slope. So it asks you, but the problem asks you for the angle of ascent. So now how am I going to go from slope back to angle? Now it's arctan, right? Because we went from angle to slope with tangent. Go from slope back to angle with arctan. So that's the slope of the branch path. So the angle of the branch path, so the angle of ascent of the branch path is the arctan. Is inverse tangent of this 0.315 in degrees. I'm just going to type it in. Arctan 0.315 in degrees. And we get 17.484 degrees. About. And that I hope is plausible. I hope it's plausible. It's like, yeah, it's a little bit shallower, right? If you go off from the maximum rate of ascent. If you kind of zigzag your way up the hill instead, you're going to go at a lower, it's an easier path, right? So you could write this as, I mean, I kind of like that you could write this as arctan of tangent of 20 times cosine of 30. That's kind of the answer in closed form. That's what it gives you. Okay, so that's kind of a way to just, you might look back over that and see. You just have to interpret everything the correct way and you'll get the right answer. All right, let's call it a day. I'll talk to Teresa about having a study group tonight if you guys want to come work on your note sheet and review stuff with her. And I do have office hours now and again this afternoon. So, all right, have a good one.